Hi everyone. So this is Dr. Swaminathan SM. Following with the previous video, we will continue this next impulse response of and step response of the second order system examples. So following with the activity, we will discuss about the percentage overshoot. So the percentage overshoot it defines the value of land percentage of maximum power shoot divided by 100 again the divided by root of y squared plus ln squared percentage mp divided by 100. So next the underdamped value we will discuss about before the underdamped value. So find the natural frequency and the damping ratio of the system. G of S is equal to 36 divided by S squared plus 4.2 S divided by 36. Compare with the transfer function omega n squared divided by S squared plus 2 sigma omega ns plus omega n squared. So you can get omega n squared is equal to 36. So omega n is equal to 6 and tau is equal to 0.35. Next, following with this example, you can get the G of S is equal to 100 divided by S squared plus 15S plus 100. Find T percentage overshoot peak time. So omega n is equal to 10 because omega n squared is equal to 100. So omega n is equal to 10. Tau is equal to 0.75. So TS is equal to 0.533S. Percentage overshoot 2.838% and TP is equal to 0.475. Next to the underdamped value second order system specifications. So you can get the underdamped value and overdamped response. R of S is equal to 1 by S and overdamped value 9 divided by S squared plus 9S plus 9. C of S, that is 2 poles and no zeros. So A is equal to 9. So you just substitute the value. A is equal to 9. So tau greater than 1. So the overdamped response, these are all the overdamped response. So the poles having left hand side of the plane. So the underdamped value, so you can get the underdamped value, that is 2 poles and 2 zeros. So you can get C of T from G of S. So S is equal to 0. S, that is minus 1.5 plus or minus J 2.598. That is 2 complex poles. So 0, that is 0 to 1, the tau is placed because it is underdamped response, and the underdamped response the value. So these are the graph representation. And next the undamped value, you can get the undamped value. C of T is equal to K1 plus K2 cos 3T. So you can get the undamped value 2 poles and no zeros. So 2 imaginary poles, that is plus or minus J3 and S is equal to 0. So this is called the undamped value because tau is equal to 0. So this is the graphical representation. And the critically undamped, that is critically damped system, you can get R of S is equal to 1 by S and C of S. So you can get C of T is equal to K1 plus K2 e power minus 3T plus K3 T e power minus 3T. So you can get easily compared with the different systems. So tau is equal to 1. So this is the graphical representation of the system. So here consolidatedly we will discuss critically damped, underdamped, overdamped and undamped graphical representation into different colors. So these are all the system, these are all the pole zero plot and these are all the response. So consolidatedly we plotted this graph comparison between the system, pole zero plot and the response. So this is the effect of the damping ratio for different positions. Tau is equal to 2, 1, 0.7, 0.4, 0.2 and 0.1. So underdamped value, it has 0 to 1 and omega n greater than 0. So you can get the two different functions for allowable tolerance and not allowable tolerance. So these are all called the delay time, that is based on the time required for the response to reach the half of the final value of the first system. So TR, TP, TS is are all the different graphical representation of the delay time and rise time also. So rise time means it is 10 to 90%, 5 to 90% or 0 to 90% of its final value. So this is called the rise time representation. And this is called peak time representation, that is the first peak of the overshoot, and maximum peak overshoot, that is maximum overshoot is the maximum peak value of the response curve measured from the unity. So C TP minus C infinite divided by C infinite, that is nothing but infinite is the final value into 100% because maximum percent overshoot. Next is the settling time. It is defined the time required for the response curve to reach and stay within a range about the final value of the size. It is specified by the special percentage of the final value. So that is called the setting time. And next is step response. That is, we just complicate this comparison C of S divided by R of S. Then you can get the step response C of S equal to partial differentiation. And make the partial differentiation, you can get the comparison. And based on the comparison, you can get the final values of the C of S. And basically, C of S, it is defined the rewritten example. So omega d is equal to omega n, root of 1 minus tau square. That is called the damped natural frequency. So from this, you can get the C of S. So C of S is equal to the value. And again, you can get the C of t by applying the Laplace inverse transform. Then you can get the C of t value and just substitute the tau is equal to 0, and you can get the C of t is equal to 1 minus cos omega n t. And again, you just substitute the value tau is equal to 0.1 and omega n is equal to 3. You can get the values of the graphical representation. So these are all the different graphical representation. So this is called the example of the second order system impulse and unit response. Thank you.